Welcome, curious minds, to our quantum deep dive.
Hello.
Today we're embarking on a really fascinating journey into the world of quantum computing. We'll be looking specifically through the groundbreaking work of a remarkable pioneer. Our mission, as always, is to extract the most important insights for you from an insightful essay by Yorgo Schneepat, making these complex ideas hopefully crystal clear.
Yeah, hopefully.
We're going to unpack the incredible story of Michelle Yvonne Simmons, a name that's really becoming synonymous with revolutionary advancements in quantum tech. So get ready for some genuine aha moments because her contributions, well, they're fundamentally reshaping our technological future in ways you might not even expect.
Indeed. And what's truly fascinating here, I think, is how one individual's unwavering focus on atomic level precision. It's almost like a philosophical commitment. How that has not only propelled an entire field forward, but actually, redefined what people thought was possible.
Right.
We'll explore her journey, her unique, almost audacious approach, and the profound implications of her work for science, technology, and really society at large.
Okay, so let's start at the beginning then. Our sources reveal Michelle Simmons was born in London in 1967. And from a young age, her family, especially her father, who was an engineer, apparently fostered this environment of natural curiosity. She wasn't just good at math and physics. She showed this exceptional, almost intuitive grasp. So how important were these early influences, do you think, in shaping her path towards such a specialized, demanding career?
That's an excellent point. You see, those early influences, they often lay the subconscious groundwork for future breakthroughs, don't they? Her academic path, starting at Durham University, where she really delved into core physics.
Okay.
And then her PhD in quantum physics at Cambridge's prestigious Cavendish Laboratory.
Right, under Professor Sir Michael Pepper.
Exactly. That wasn't just a progression of degrees. It was a deliberate immersion, you could say, in environments where fundamental questions were always on the table, where the very nature of reality at its smallest scales was constantly being probed. That foundational period, it really steeped her in the precise, rigorous thinking you absolutely need for quantum mechanics.
And it was at Cambridge then that she really started carving out her niche. She specifically looked into electron interactions within solid-state materials. Now, that sounds incredibly specific, but our source highlights it as laying crucial groundwork. How did that environment, described as a melting pot of ideas, fuel her determination to tackle scientific challenges that back then must have seemed almost insurmountable?
Absolutely. And maybe think of it less as a narrow niche and more as the crucible where her future approach was forged. Her work there, understanding how individual electrons behave inside a solid, that provided the bedrock, really, for comprehending electronic properties in nanoscale materials. The Cavendish Lab, it's known for its Nobel laureates, its groundbreaking discoveries in quantum physics. It wasn't just a place to learn, it was a place to question.
Right.
And this fostered a deep understanding of the quantum world, sure, but also, importantly, a profound belief that with enough precision, you could not just observe quantum phenomena,
but actually control them.
Exactly. Control them. And that belief, born in that melting pot, it really became a driving force throughout her entire career.
Okay, so building on that PhD foundation, she continued her postdoctoral research at Cambridge, still focusing on electronic properties and nanoscale materials. But what's interesting is her focus shifted a bit towards developing experimental techniques for precision measurement of quantum effects. That sounds like a key step beyond just theory.
It really was. Postdoctoral work is often where scientists truly hone their unique experimental methods. Her early publications from this period, particularly on single electron transport mechanisms in semiconductor nanostructures, they were pivotal.
What does that mean, practically?
Well, to put it simply, she was studying how you could move individual electrons through incredibly tiny wires or structures, sort of like channels, without losing their quantum information.
Ah, okay.
This research highlighted conditions for near-lossless electron transport in quantized systems. So imagine electricity flowing with almost zero resistance, but at a quantum scale where the electron's quantum properties are preserved.
Wow.
This was absolutely crucial for quantum applications because, you need to move quantum information reliably.
Yeah.
It showed that controlling electrons at such a fine level wasn't just theory anymore. It was becoming experimentally tangible.
So after this really foundational work, she made a big move, a strategic move, it sounds like, in 1999 to the University of New South Wales, UNSW, in Sydney. Our sources indicate she wasn't just looking for a new job. She sought a very specific environment. What was she after? What did she aim to achieve by building her own team there?
Yeah, this move was a masterstroke, really,
Oh.
a testament to her long-term vision. She wasn't content merely contributing to existing labs. She wanted to build a whole research ecosystem from the ground up,
Right.
dedicated to her unique, highly ambitious research agenda in nanotechnology and quantum physics. She needed the freedom, the resources, to pursue quantum computing in a way few others were considering at the time.
Which was?
Through atomic-scale precision in silicon. Her decision to move really positioned Australia, perhaps unexpectedly to some observers back then, as a future leader in this cutting-edge field.
So she didn't just join an existing structure.
No, she became instrumental in establishing what would become the Australian Research Council, or ARC, Center of Excellence for Quantum Computation and Communication Technology. And this center wasn't just another lab. It quickly grew into this international hub, attracting top-tier global scientists, fostering vital interdisciplinary collaboration across physics, chemistry, engineering, computer science.
All under one roof.
Exactly. It was a conscious effort to bring all the necessary pieces together.
And it's here in Australia where her really revolutionary contributions started to shine, specifically with her intense focus on silicon-based quantum processors. Our sources describe silicon as one of the most promising platforms, but why silicon? It seems counterintuitive compared to, say, superconductors. And what were the main challenges she and her team faced?
Yeah, the choice of silicon was strategic, and maybe surprisingly counterintuitive, like you said. While many others were exploring superconducting circuits or trapped ions, Simmons recognized silicon's potential for scalability.
Ah, the manufacturing aspect.
Precisely. It's the backbone of our classical computer industry, right? So there's this mature manufacturing infrastructure already in place. Huge advantage. The challenge, however, was immense. How do you control individual qubits at an atomic level with extreme precision and stability? The biggest hurdle was decoherence.
That's the loss of the quantum state.
Exactly. That's when a qubit, which holds quantum information in its fragile quantum state, just loses that information because it interacts with its environment. Stray, heat, noise, vibrations. It's like trying to balance a spinning plate on a stick in an earthquake.
Okay, difficult.
Very. Her breakthrough was truly revolutionary. It involved using scanning tunneling microscopy, or STM.
Okay, what's that?
Imagine an atomic-level robotic arm. So precise, it can not only see individual atoms on a surface, but also pick them up and place them exactly where you want them.
Seriously?
Yeah. Simmons and her team used STM to precisely place single phosphorus atoms within a silicon substrate, and then critically demonstrate that these single atoms could actually operate as stable qubits.
Wow.
This wasn't just theoretical. She demonstrated experimental protocols to actually read and manipulate their spin states, basically turning a single atom into a functioning switch that holds quantum information.
That's mind-boggling. Placing individual atoms with less than a nanometer of accuracy, and then creating what's often called the world's first single-atom transistor. It sounds like science fiction. What are the deeper implications of that? Miniaturization down to a single atom. What does that mean for us?
Well, it fundamentally redefines the physical limits of miniaturization.
Yeah.
A single phosphorus atom acting as a transistor. I mean, we're at the absolute smallest scale possible for such a device.
Right.
Now, this isn't just relevant for quantum computers, although it's certainly foundational for building them. Its true significance stretches to the entire semiconductor industry. For decades, we've been shrinking transistors, right? Moore's law, packing more onto a chip.
Yeah.
Simmons's work suggests a path to components far smaller, potentially far more powerful than anything we can currently envision, pushing past those traditional limits.
So smaller, more efficient devices in the future.
Potentially, yes. Radically more efficient and dense. Her work also really stands as a prime example of the power of interdisciplinary collaboration. You need chemists for the materials, physicists for the quantum mechanics, engineers to build the devices, computer scientists for the algorithms.
No single field could do it alone.
Absolutely not.
Okay, so beyond the sheer scientific brilliance in the lab, Michelle Simmons also took on these significant leadership roles. You mentioned she was instrumental in founding and leading the ARC Center. Can you tell us a bit more about its specific goals and achievements under her guidance?
Yeah, the center's goals were, well, nothing short of putting Australia right at the forefront of global quantum research. They focused on 3 pillars: developing these atomic precision quantum processors, building secure quantum communication systems, and crucially, creating these interdisciplinary platforms to foster talent and collaboration.
And they delivered.
Under her leadership, they didn't just aim high, they absolutely achieved it. They developed the world's first silicon-based quantum processor, and of course, that single-atom transistor we just discussed. These aren't just academic papers, They are tangible steps toward real-world quantum technologies, all built on her philosophy of extreme precision.
So beyond the hardware breakthroughs, it sounds like she also really championed developing the next generation of scientists. That's a different kind of impact, isn't it?
Oh, absolutely.
What kind of programs did she put in place to make sure this long-term vision was sustainable?
Yeah, her long-term vision isn't just about the immediate scientific breakthroughs. It's about transforming entire industries for decades to come. Think cryptography, material science, medicine, AI.
Huge potential.
Immense. She recognized that building these quantum technologies requires not just brilliant minds today, but a sustained pipeline of talent for the future. So she spearheaded comprehensive programs, doctoral scholarships to attract the brightest young minds, postdoc positions to deepen their expertise, robust mentoring initiatives.
Investing in people.
Exactly. She firmly believes silicon is the key for scalable, economically viable quantum computing. And she articulates this forward-looking perspective passionately in her lectures, like the one at the Lindo Nobel Laureate meeting in 2017.
Yeah.
And in influential publications, like her Nature paper on the single-atom transistor. She even made these really complex scientific ideas accessible to a broader audience through her TEDx talk.
Making it understandable.
Yeah, and that commitment to nurturing talent ensures her legacy extends far beyond her own lab bench.
It's clear her impact goes way beyond just academic research and papers. She's received a whole host of prestigious awards. Can you highlight some of the most significant ones and explain why they're not just personal accolades, but actually important for quantum research awareness?
She has indeed. Among her most significant, being named Australian of the Year in 2018. That's a tremendous public honor.
Yeah.
She also received a fellowship of the Royal Society in 2017, placing her among the world's most eminent scientists. Plus, the Walter Boas Medal, the Thomas Rankin Lyell Medal, the Eureka Prize for Leadership in Science.
Quite a list.
It is, and these aren't just individual recognitions of her brilliance. They significantly elevate the public consciousness about quantum research, and crucially, about Australia's burgeoning role in it. When a figure like Michelle Simmons is celebrated so publicly, it draws attention, investment to the entire field. It inspires future scientists. It inspires policymakers.
And her influence on the next generation, especially women in science, that seems like a powerful, maybe less talked about part of her legacy.
Oh, definitely.
What stands out about her role as a mentor and a champion for greater inclusion?
Her role as a mentor and advocate is profound. She doesn't just foster innovation. She actively challenges established paradigms. As a leading woman in a field that's historically been dominated by men, her very presence is a powerful statement. She actively champions gender equality, inspires young women through her public talks, and perhaps even more effectively, just through the undeniable power of her own career as a living example. And it raises that important question for all of us, doesn't it? How much faster can scientific progress be? How many more breakthroughs can we achieve when we truly include and empower all voices, all talents, regardless of background? Yeah. Her public science communication, like that TEDx talk, isn't just about explaining quantum physics. It's about showing young people, especially young women, that they too can lead in these complex, demanding fields.
Okay, so despite all these incredible breakthroughs, the momentum she's built, the road ahead in quantum computing still has significant hurdles.
Oh, absolutely.
What are the key challenges that remain? And how is Simmons, in particular, strategically approaching them?
The challenges are formidable. Decoherence, as we mentioned, remains a primary obstacle. Qubits are inherently fragile. They lose their quantum state very quickly, which limits computation time. Then there's scalability. Moving from working with, a handful of qubits to the thousands or even millions needed for really powerful quantum computers. That's a huge engineering and physics challenge.
Right.
Material science limitations are also a factor, and developing practical quantum algorithms that can actually leverage these machines effectively. That's another whole area of open research.
So how is Simmons tackling these? What's her strategy?
Well, what's fascinating is her unique strategic approach. While others might be exploring different qubit technologies, she sort of doubles down on what she calls atomic precision. Her belief is that by perfecting the placement and control of every single atom, they can intrinsically minimize decoherence, make the qubits inherently more stable from the get-go.
Building quality in from the start.
Exactly. She's developing specific error correction mechanisms tailored for silicon, rather than relying on more general approaches. She fosters that intensive interdisciplinary collaboration, recognizing no single field has all the answers. And crucially, she's exploring innovative scaling architectures, thinking about things like stacking designs in 3D to overcome the physical limitations of current 2D chips. It's a holistic, incredibly focused strategy.
And this strategic approach focused on silicon and atomic precision. This must have direct relevance for future applications, right? Connecting it to the bigger picture, how will her work impact actual industries, solve real-world problems?
Oh, it's foundational for transforming industries. In cryptography, for instance, quantum computers could revolutionize security.
How so?
Well, potentially by breaking current encryption methods, think Shor's algorithm cracking RSA keys, the stuff that protects our online banking, emails.
Gary.
But also on the flip side, by enabling entirely new quantum-resistant encryption methods, securing our digital future against future quantum threats. In medicine, they could simulate complex molecules, drug interactions with unprecedented accuracy, dramatically accelerating drug discovery, personalized medicine. For AI, quantum machines could process massive datasets, solve optimization problems far beyond what classical computers can manage, revolutionizing logistics, machine learning, finance.
Whoa.
And in material science, designing novel materials for sustainable energy, better batteries, new catalysts. Her work isn't just about computing, it's really about unlocking capabilities that are currently impossible for us.
So with all this groundbreaking work, this strategic foresight, what does it all mean for Australia's position in this incredibly competitive global race for quantum supremacy?
Australia, thanks to visionary leaders like Michelle Simmons and the sustained investment behind her, is undeniably a key player, a serious contender. They have a smart two-pronged strategy. Significant national investment, making sure researchers have the resources, coupled with robust international collaboration.
So competing and collaborating.
It's exactly. Their niche in silicon-based quantum computing, with its unwavering emphasis on atomic precision, gives them a unique competitive edge, especially in a field with heavy investments from the US, China, the EU. Simmons herself, she sees this global competition not as a zero-sum game, but actually as a powerful impetus for collaboration, pushing the boundaries of what's possible for everyone. She's building not just a lab, but an entire national ecosystem around this tech.
Right. So as we wrap up our deep dive into the incredible contributions of Michelle Yvonne Simmons, it's just clear her work is nothing short of revolutionary. From her early fascination with physics to precisely placing single atoms, then leading a global research hub in Australia, she has profoundly impacted our fundamental understanding of quantum physics and really accelerated the whole trajectory of quantum technology.
Her journey is such a powerful reminder, isn't it? That fundamental research, when it's coupled with visionary leadership and this unwavering, almost audacious commitment to precision, truly can transform our world. Her dedication to overcoming these seemingly intractable technological hurdles and fostering future generations of scientists, that's just as inspiring, I think, as her groundbreaking scientific discoveries.
Yeah, what truly stands out from this deep dive for me is that relentless pursuit of precision. It just defines her work. The idea that by controlling the very smallest building blocks of matter, we can unlock capabilities that seemed, well, impossible just decades ago. Perhaps it's the thought that one day, thanks to pioneers like Simmons, we might see computations that are currently unfathomable become, commonplace, solving some of humanity's most complex challenges. Climate change, incurable diseases.
It's an exciting prospect.
It really is. We hope you've enjoyed this fascinating exploration of Michelle Yvonne Simmons' immense impact on quantum computing based on Jurgo Schneppat's insightful essay. If you'd like to explore more about these topics, you can visit schneppat.de. That's SCHNEPPAT.de. Until next time, keep digging deeper. Bye for now.